In 1917, Einstein called it his greatest blunder, but decades later it turned out he might have been right. The cosmological constant, a mathematical term Einstein slipped into his equations to hold the universe static. He believed the cosmos was eternal, unchanging. When mounting evidence in the 1920s showed that galaxies were flying apart, he abandoned the term, calling it his worst mistake. Yet in 1998, astronomers resurrected that very constant, renamed dark energy, to explain why the universe is not just expanding, but accelerating. In November 1915, Einstein unveiled his general theory of relativity, a new understanding of gravity as the curvature of space-time. When he applied it to the universe as a whole, he found a problem. Gravity's pull would cause everything to collapse inward. But the prevailing view, rooted in Aristotle and Newton, held that the universe must be static and unchanging. Determined to reconcile his theory with this belief, Einstein added a fudge factor to his field equations, the cosmological constant, denoted by the Greek letter lambda. This constant represented a repulsive force intrinsic to space itself, just enough to counteract gravity and keep the universe balanced, neither expanding nor contracting. His 1917 paper introduced lambda as a natural feature of space-time, not an ad hoc patch. In 1929, Edwin Hubble published observations of distant nebulae, we now know them as galaxies, revealing a direct relationship between their distance and their redshift. Every galaxy, on average, receded from us. The farther away, the faster it moved. Hubble's law implied the universe was expanding, running counter to a static model. Learning of Hubble's discovery, Einstein reputedly remarked, "If there is no quasi-static world, then away with the cosmological term." He discarded lambda, letting his equations predict cosmic expansion. The constant faded into obscurity. Cosmologists focused instead on mapping the rate of expansion, the Hubble constant. For the next 70 years, most theoretical work ignored lambda. The dominant Big Bang model described a decelerating expansion. Gravity should gradually slow cosmic growth. Observational cosmology aimed to measure that slowdown and determine whether the universe would collapse in a big crunch, coast forever, or sit at a critical balance. Astronomers refined measurements of galaxy distances, cosmic microwave background radiation, and the abundance of light elements, yet precision was limited. Uncertainties in supernova luminosities, galaxy motion, and cosmic structure blurred the picture. The question remained unresolved: would gravity eventually win? In the mid-1990s, two teams of astronomers, Supernova Cosmology Project, led by Saul Perlmutter, and High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, set out to measure cosmic deceleration by observing distant Type 1a supernovae. These standard candles shine with known intrinsic brightness, letting researchers gauge their distances precisely. When both teams published in 1998, they found a shocking result. Distant supernovae appeared fainter than expected in a decelerating universe. They were farther away than the old models predicted. Instead of slowing down, cosmic expansion was accelerating. To explain this, scientists reintroduced a positive lambda, reviving Einstein's cosmological constant as dark energy, a pervasive pressure that drives space-time apart. This discovery won the 2011 Nobel Prize in Physics and upended cosmology. Today, we estimate dark energy makes up about 68% of the universe's total energy density, with dark matter at 27% and normal matter at a mere 5%. Physicists still debate the nature of dark energy. Possibilities include vacuum energy, quantum fluctuations give empty space a baseline energy density equivalent to lambda, quintessence, a dynamic field that changes over time, unlike Einstein's constant, modifications of gravity, general relativity might need tweaks on cosmic scales, Clyde future missions like the Euclid satellite, the Nancy Grace Roman Space Telescope, and ground surveys such as LSST aim to map cosmic expansion and structure growth with unprecedented precision. Observations of galaxy clustering, weak gravitational lensing, and the cosmic microwave background will constrain dark energy's properties and test whether lambda truly is constant or if new physics awaits. Einstein's biggest mistake turned out to be one of his greatest insights. That elegant cosmological constant, conceived to preserve a static universe, now stands at the heart of our understanding of cosmic fate. As we probe deeper into dark energy's mystery, we continue Einstein's legacy, daring to rewrite the equations that describe the grandest stage of all, space-time itself. What do you think dark energy really is? Drop your theories below. And if you enjoyed this journey through Einstein's greatest blunder turned revelation, hit subscribe for more cosmic deep dives.